Okay, so chapter 10, problem number 23, which says, what fraction of a piece of iron will be submerged when it floats in mercury? Doesn't tell you anything about the mass of the iron, doesn't tell you anything about the volume of the iron, so let's see how much progress we can make. Imagine that you've got some bucket of mercury. Here it is. And apparently, floating in it is a piece of iron. Now the good thing is in the textbook we have a table of densities of different materials. So presumably this whole question can be answered just by knowing the density of mercury and the density of iron. It must be, otherwise how in the world could we possibly solve this? Remember when you've got things that are floating, some fraction of that object is under the fluid, and some of it is out in general. And so why don't we go ahead and sort of draw it like this. So this fraction here, this amount here, if you like, this is V, let's call it VD, the displaced volume. Okay, the amount of the volume of mercury that was moved out of the way to make way for the iron. The full piece of iron has a full volume, let's just call that V. And these densities of mercury and density of iron those are quantities that we can look up. Okay, so at least that's what the picture looks like. And we're trying to figure out what fraction of iron will be submerged. In other words, what our goal is. The goal is to somehow get VD over V, right? That's the fraction submerged. Okay. Conceptually, well, we're dealing with a solid object in a liquid, so we could be dealing with some sort of fluid mechanics. We probably are. So we're dealing with fluids, which probably means we have to deal with density and might mean that we have to deal with pressure. But specifically, we've got something that's floating. So that should be a key point to go to your notes or thoughts about buoyancy. Okay, in other words, we have a buoyant force. So the primary equation that we're going to need here, equations, would be the buoyant force, FB. And remember, this is given by, there's a couple different ways to write it. You can either write this as MF times G, where MF is the mass of fluid that was displaced. So right, in order to make room for this amount of submerged iron, some volume of mercury got pushed out of the way. The mass of that mercury that got pushed out of the way, if you take that mass multiplied by G, that'll tell you how much force the mercury is providing and that's pushing up on the iron. Another way to write this is, if you don't, let's say, have direct access to the mass of that fluid, you can write it as the density of that fluid. Again, in this case, it's going to be mercury, times the volume that was displaced. In other words, that's VD. That's the same VD here. Multiply that by G. And we'll see which one is most useful for us. Okay. Well, we're dealing with forces. We might as well try to draw a free body diagram and see if that is helpful at all. We have some piece of iron which has some mass. I'm just going to write it as M iron. And let's see, it's on Earth or some planet, so there's some gravity pulling down on it, Fg, and that's equal to the mass of iron times G. And apparently there's also a buoyant force, Fb, and we can write it in either of these two ways. Now the thing is floating, which means that the up force and the down force must cancel. If you like, you could go ahead and use Newton's second law. We might as well go ahead and practice this. It's always a good thing to do that. The buoyant force minus the force of gravity is equal to the mass of iron times the acceleration of that iron. It's not accelerating. The whole right-hand side is 0, and that tells you that the buoyant force is equal to the gravitational force. Okay, that's the reminder. That's how you know it for sure, because Newton's second law tells you. Okay, the buoyant force is equal to the force of gravity. Let's go ahead and plug in the things that we've got. The buoyant force, let's write it in terms of densities, because my suspicion is, since they didn't tell us about the mass or volume of any of this stuff, this whole problem can probably be solved with density. So density of fluid times the displaced volume of the mercury that got out of the way for the iron, times G, that's the buoyant force, equal to the force of gravity, which is the mass of the iron, times G. So here's where we should go ahead and make the next step. We don't know the mass of the iron. We might as well try to write it in terms of density. The mass of an object can be written in terms of its density. If you recall that density is defined as mass over volume. So the mass must be density times volume. Okay? So the mass of this iron must be density of iron times the volume. It's the volume of the whole piece of iron, not just the part that's displaced, if you're going to get the entire mass of that piece of iron. So this is V, okay, times G. As oftentimes happens, the G will end up canceling. And what you're left with is an equation that involves rho F, rho iron. Those are numbers we can look up. And then we've got a VD and a V. And remember what our goal was, to get the ratio of displaced volume to full volume. So now we can do it. Let's go ahead, and if we want to get VD over V, let's divide by V on both sides and divide by the mass of the fluid, or the density of the fluid. That would tell you that VD over V, this is what we want, is equal to rho iron over rho of the fluid. In other words, the mass of the density of the mercury. In your textbook, you can look up, or on the internet, the density of iron comes in at a whopping 7.8 times 10 to the 3 kilograms per meter cubed. In other words, it's 7.8 times higher than the density of water. But mercury is even higher than that. Mercury comes in at 13.6 times 10 to the 3 kilograms per meter cubed. Therefore, this ratio, which comes out to be about 0.57, telling you that the fraction, I'll go ahead and write that as multiply by 100 to get your percentage. 57% of the piece of iron should be submerged. And does that make sense that not all of it is submerged? Yes, the density of iron is lower than the density of mercury, so some amount of it will stay above the fluid.